Welcome back to our study of the derivative and how it measures an instantaneous rate of change. And again, a lot of problems, a lot of times people are interested in how things are changing. And that's why we're interested in the derivative. I gave you an application of what your instantaneous velocity could be referred to as speed if you're going in one direction and not turning around. So your speedometer measures a derivative in some sense. In your last con video, we defined this as you can define a derivative again. We used the limiting process, and now instead of putting in a number like 3 for x and 3 up here, we're going to take the derivative at any point x. So in this section we talk about the derivative as a function. In the con example, he used the function of x squared, which I drew down here. Here's your function here of x squared. Again, a common function that you know. Through the limiting process, define that the derivative was equal to 2x. Okay, that's 2x. So you can look at the derivative here in red. It's just another function, right? The derivative here is another function, and notice this is a function. It's a line, passes through the origin, and what does it tell us? It tells us at any point on this line, it tells us the slope of the tangent. So down here you can see the slope of the tangent line here is negative. Here at 0, the slope's 0, and here the slope is positive. Since this first derivative function, it's just a function itself, well, you might think, well, can't we take the derivative of the derivative? And you'd be correct. You'd be correct if you thought that. So if I wanted to write down here, well, what's the second derivative? We might write it down like this. The second derivative at x, which just happens to be the derivative of the first derivative. Now, I'm not going to use the limiting process here. I'm going to apply just remember the derivative, this is the derivative of the red line here. The derivative gives instantaneous slope of the line. Well, what is the instantaneous slope of a straight line? Well, here, since it's just a straight line, hey, the slope is constant. The slope is just 2. So this, you would see, the second derivative of this function here is 2. It's just a constant. How would I draw that? Well, I'll change my colors, put that in green here. So we can take higher order derivatives, and I might label this function the second derivative at x, and here it's just equal to 2. Well, it's a function, is it not? It's the second derivative, or it's the first derivative of that function. What would you think the third derivative would be? The third derivative, can you give me that without using a limiting process, just with a little logic? Because we're going to, if I looked for the third, 1, 2, 3, let's draw it that way. That's just going to be what? Well, that's going to be the instantaneous slope of the derivative gives you instantaneous slope. What's the instantaneous slope of that line? Doesn't change. Looks like it's 0. Sure enough, that's 0. And I could draw that again, but I mean, that would be just a straight line here. Okay? So, the derivative can thought to be a function, and it gives you the slope of the tangent line. Here I wanted to go through kind of quickly some notation you might see when we talk about derivative operators, because a lot of times in calculus the real problem people have is reading it or understanding what the question is asking. So it's kind of important that if I write something a different way, you know what I'm talking about. So here, remember I could say, well, y is equal to f of x. Might write down a function like that. We're always talking about functions in calculus. And I wrote down derivative operators like what? Well, I might say, well, that's f prime. here's a way to write. What does that mean? I want the derivative of that function f of x. That's one way to do it, comma. Another way you might see, I might write it like this, y prime. These are equivalent. These things are equivalent. I take the derivative of y. It's just kind of assumed y as I'm taking it as a function of x. You also might see it written down like this. This takes a little more work, so I'm not as big a fan of it. But here it is. This is telling me the change in y over the change in x. But it does remind you this is a ratio. It's a limiting ratio of the change in y over the change in x. Those are the most common. Sometimes you might see a derivative operator like this. You know, I might write, okay, I'm taking the derivative, big D of f of x, not as common. Or when you get into two-dimensional things, they might tell you, I want the derivative with respect to x of, say, f, okay? But these are the more common ones. So notation, again, it's not a trivial thing. Make sure you can read what this means. Being able to read functional notation, derivative notation. If you have any questions about that, please see me. Okay, we've done a little bit of work now defining what a derivative what it is, and the intuition behind it. Now I'd like to talk a little bit about when does a derivative exist at a point. So just when we talked about, when we should talk about limits, how do you take a limit? When does a limit exist? But let's look at this. Here's the definition of a derivative, right? The derivative of function is equal to the limiting process. When does that exist? Well, it exists when the limit exists. How does a limit exist? A limit has to exist if the limit from the right side is equal to the limit from the left side. Remember? So this limit better be equal to h coming in 0 from the positive side of, and I'll just call that delta x over y. That better be equal to the limit as h goes to 0 from the negative side, right? That has to be true. Now we could do it algebraically. I think the more intuitive way is to give you an example and do it graphically. Let's use our favorite example for these kind of problems is an absolute value function. So let's do that. Let's again, remember all these functions you need to be able to draw and know. Remember how we started the class off with that? Maybe you're starting to get a feel for why that is the case here. Okay, so here's my absolute value function. Now think about what a derivative is. If I wanted to take, if this was equal to y was equal to that, or if that's equal to f of x, what would f prime of x look like? What's f prime of x look like? Well, let's get a different color here. How about we go up to blue? What is the slope of this line over here? What's the slope of this line here? Well, we know this is just equal to negative x, is it not? That's equal to negative x. That's equal to positive x. So over here, the slope is negative 1. So it looks like that. So it's equal to negative 1 when x is less than 0. What happens as x is greater than 0? Well, here, this slope, that slope is just positive 1. Positive 1 when x is greater than 0. Well, what happens at 0? What about here? What about there? Does the derivative exist at that point? And the answer, if you take the limit from the left and the right, on the left side it's -1, on the right side it's +1. Again, we could do it algebraically very rigorously, but I think you can see intuitively that f prime does not exist at x equal to 0. So this is a very sharp point right here. I like to say you got to be careful around that. If that point really existed, it is instantaneously sharp. So you really could cut your finger real quickly here, so be careful. This is sharper than any Cutco knife you've ever seen. In reality, very tough to make a surface that sharp. But on our theoretical function of x prime, the derivative does not exist. Okay, here's some other examples you should be familiar with in which the derivative does not exist at a particular point. Okay? First one is similar to one we showed before. Anytime a real sharp point, if I drew something like that, and this was an instantaneously sharp point where the derivative went from positive to negative, this would not, at this point C, the derivative would not exist. Okay? That would be one. The second one over here, anytime I have a function that's not continuous, if the function is not continuous, as here, if it's not continuous, it's not differentiable. Not continuous, not differentiable. You also could have, so this might be a case where a sharp point, here it's not continuous. Here you could kind of have what I'd call maybe a vertical free fall. Maybe you'd have something, try it like that. Okay, so here's where the tangent line in this case, the tangent line has an infinite slope. Okay, so at this point here, C, the derivatives that derivative wouldn't exist there either. Okay, so 3 examples where a derivative doesn't exist, and it has to do a little bit with smoothness here, with the smoothness. Not a smooth function, or here actually we have kind of vertical, what we might call a vertical tangent, where the derivative here is infinite. Okay, I wanted to briefly tie this concept of a derivative existing back to this little kind of fun drawing I made earlier, where we talked about the smoothness. We talked about the smoothness of a function at a point C. Okay, and you'd start off, remember the smoothness range gets smoother and smoother as we go left to right. And if it's this smooth, then it implies it's that smooth. So we start off and we say, well, just to be smooth at all, the limit has to exist. The limit doesn't exist at C. It's not a smooth function. Okay? If it's a little smoother than that the limit might exist, then it might be continuous. Continuous at point C. Okay, if it's continuous at point C, well, if it's continuous, then the limit exists. Well, if it's a little smoother than just being continuous, you might say, well, f prime at C exists. Okay, the derivative exists. If the derivative exists, it must be continuous, and the limit must exist. Well, then we could go to higher order derivatives that we said, well, if it's even smoother than the first derivative, maybe the second derivative exists. The second derivative exists, well then the first one does, it's continuous, and it just gets smoother and smoother, and then we could go into much higher order derivatives. That's the third order derivative. And again, you can see as these things exist, the function gets smoother and smoother at a point C. And you'll see a lot of multiple choice questions where they expect you to know these properties of a function and how it means if the second derivative exists, well, certainly the limit must be there.